All right, let's look at finding vertical asymptotes and holes in graphs. So let f of x be a rational function and let a be a number that's not in the domain. So a, if you plug it in, makes the denominator 0. Our question here is, how does the graph behave at x equals a? And the answer is it either has a vertical asymptote there, or it has an open circle, which I call a hole in the graph at that point. And we saw an example of this in the previous video, but here's another example. We've got a quadratic here over x squared minus 9. This thing has a vertical asymptote here at 3. And back here at negative 3, there's actually an open circle in the graph. It doesn't show up on Desmos unless you zoom in on it and click it. But there is an open circle there. And let's look at how to find that. Well, actually, I've got that down here, but let's, I want to do it on this problem too. What we can do is factor this. Now the bottom factors into x minus 3, x plus 3. The top factors into, let's see, we got 3 and 5, x plus 3, x plus 5. All right, and notice the plus 3, x plus 3 cancels. Notice this right here gave us x equals 3. This gives us x equals negative 3 as numbers that we have to exclude from the domain. Now, the one that remains here after the factoring, this gives us the vertical asymptote. The one that canceled away, this one gave us the hole. And so that's how you determine if you get a vertical asymptote or a hole. To find the holes in VA of a rational function, factor both of them. Set b of x equal to 0. And the solutions to that will tell you where all the holes and vertical asymptotes are, but it doesn't tell you which are which. To figure out which one is which, what you do is you cancel as much stuff as possible, and the zeros of the remaining denominator give you the vertical asymptotes, and the ones that canceled away give you the holes. So let's look at this example. We're going to do this one without even looking at the graph. Find the holes and vertical asymptotes of this. All right, the top of this factors into x plus 1, x minus 1. Okay, the bottom, that's a cubic. We can't factor cubics in general, at least not easily, but this one we can factor because we can factor out as an x. And then we can factor this as if it were a quadratic. We need numbers that add up to 9 and multiply to 14. So 2 and 7. All right. This gives us 3 numbers. X equals 0, x equals negative 2, and x equals negative 7. Excuse me. None of those cancel away, though. So all 3 of these give us vertical asymptotes. And no holes. All right, what about this guy? This one, if I factor it, let's see, the top, 7 and 12, 3 and 4, will that work? Yeah, x minus 3 and x minus 4, those add up to negative 7, multiply to positive 12. And on the bottom, let's see, x minus 3 and x minus 5, those multiply out to 15 and add up to negative 8. So for this we get x equals 0, x equals 3, and x equals 5. This one cancels away, and so the ones that remain give us vertical asymptotes, and the one that canceled away gives us a hole. All right, this next one, it looks like it's an ugly problem because it's got so much stuff in it, but the fact that it's been factored for us makes it easy. If we look at this, we're going to get x equals 3, x equals 5, x equals 7 and x equals 11. Now let's cancel everything we can. Let's see, x plus 3 doesn't cancel. X plus 5 cancels with one of these. X plus 7 squared cancels with two of those, and the others remain. So these two that cancel away gives us wholes, and the ones that didn't cancel away give us vertical asymptotes. All right, that's the end of this section, but there's one more thing I want to talk about just briefly, and that's the difference in two functions. Not differences in subtraction, but differences in two different functions. I'm going to zoom way in here. This is going to be very small when I zoom out, but no problem. Well, let's say you have the graph, the function f of x equals x squared plus, I'm making this up as I go. On the bottom I'm going to have x plus 1, and on the top I'm going to have x squared plus 5x plus 4. Now if you look at this, you can factor it into x plus 1, x plus 4 on top, and then just x plus 1 on bottom. So we've got that function, and then we've got this function, g of x. I'm going to get this by canceling this, just x plus 4. Now, technically speaking, f of x and g of x are not the same function. The only place that they differ, though, is that f of x has a whole at x equals -1. Other than that, these two functions are exactly the same. But we would consider them to be two distinct functions, not equal to each other, because one of them has a whole and one doesn't. That's one of those things that's it's kind of important if you want to do like rigorous proofs of stuff later on. It's not terribly important right now, but technically those are different functions, and I just wanted to point that out. You know, you can install a function in a, you can install a whole in a function easily. I'm going to do this on Desmos. So give me a function. I guess that doesn't work when I'm doing this online instead of in class, but let's say we have this function and we wanted to install a whole at the point, it needs to be some point on the function, let's say at the point 3,9. The way you do that is you take the original function up here, x squared, and you'd multiply it by x minus 3 over x minus 3. We can't really see it unless we come in here, and now 3 undefined. So if you want to install a whole in a function, that's all you've got to do is whatever the x coordinate is, you multiply x minus that over x minus that and install a whole. If we wanted to install a whole at the origin, we just go ahead and multiply this by x over x. And now this graph also has a whole at the origin. Of course, to see it, I need to be able to click on it. There we go. 0 undefined. All right, so that'll do it for this, this video.